Hello, and welcome to MacMod Analytical's hosted webinar series entitled Increased Sensitivity and Solvent Savings with Novel 1.5 millimeter ID Stainless Steel Columns. I'll be your moderator today, Jeff Faden. MacMod Analytical is a well-known chromatography solutions provider serving the life sciences market since 1986. We are widely known as a preferred vendor for HPLC and UHPLC columns and accessories, GC columns and accessories, HPLC lab safety equipment, among many other products. We are very excited today for today's talk from Advanced Materials Technology, a company we have been representing since their inception in 2006. Advanced Materials Technology has continued their storied history of innovation, and today's talk is another example of that. I want to remind our attendees that if you have any questions during the presentation, please type them into the question window and include your name and company info. We will do our best to answer as many questions in the allotted time as possible. Our speaker today is Stephanie Schuster from Advanced Materials Technology. Dr. Schuster earned her PhD under the guidance of Professor Joe P. Foley at Drexel University. She joined Advanced Materials Technology, AMT, in June 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptides and protein separations. Most recently, as part of the technical support team at AMT, Stephanie has been providing customers support in optimizing and troubleshooting their applications. Thank you for joining us today, Stephanie.
Thanks, Jeff, for the invitation to present here today, and thanks to everybody for joining us. So I'll start with a brief outline of the presentation. First, I'll talk about the desire to move to smaller ID columns. Then I'll go into the benefits of smaller IDs with the novel 1.5 millimeter ID UHPLC stainless steel columns, and then we'll have time for a Q&A session. So first, I wanted to give a little bit of background on the move to smaller ID columns. So originally, HPLC columns were 4.6 millimeter ID, and they were normally operated at 1 mil per minute and above. Then 3 millimeter ID columns were introduced as a means to save solvent. So for example, 47% solvent could be saved going from a 4.6 by 100 millimeter column running at 1.5 mils per minute to a 3 by 100 millimeter column operated at 0.8 mils per minute. So when people saw the solvent savings going to smaller IDs, they were excited. And then of course, short columns with 2.1 millimeter ID columns were introduced for use with UHPLC and for interfacing to mass spectrometers. So some of the impacts of smaller ID columns include the effects of viscous friction are diminished, and I'll explain that in the next few slides. You'll see the signal intensity is increased when the same sample concentration is used. And then, of course, less solvent is consumed, which reduces the consumable and the waste disposal cost. So first, I'll talk about the fundamental effects in transitioning to smaller internal column diameters with respect to viscous friction. So what people have found is that thermal gradients are formed due to viscous friction. And this can be measured according to the power equation here at the top of the slide, where power is equal to the flow rate times the pressure drop across the column. So you have both axial gradients, which is where the column is cooler at the head and hotter at the outlet. And then there are radial temperature gradients where the column is hotter in the center and cooler at the wall. And I'll describe each of these in detail in the next 2 slides. So the formation of those axial thermal gradients due to viscous friction happen when you're in these quasi-adiabatic environments. So that would mean you have insulated columns or still air oven conditions, which means there's no convective movement from the oven fan. And the impact of that you can see in this plot here on the left-hand side, where we're plotting the retention factor versus flow rate. And although you have high efficiencies here, what's happening is these retention times are not as reproducible across this higher flow rate range. And that's because as you run at higher flow rates, you increase the back pressure, and that increases the power of the heat that's generated. So the trouble with this is that you would get those irreproducible retention times. The next kind of gradient is a radial thermal gradient, and that's where you have these quasi-isothermal environments with an air or water jacketed column or forced air oven conditions. And this is from the convective movement from the oven fan. So like I said earlier, the center of the column is hotter and the outside wall area is cooler. So what that means when you have a flowing water jacket, now this is a plot of reduced plate height versus linear velocity. You can see at the higher linear velocities with the flowing water jacket, you're losing efficiency. So what that means is that as you run at those faster flow rates, the efficiency drops off. Whereas where you just have the column oven, you don't have as much of a loss in efficiency. So in order to sort of mediate these two effects, people had considered going to smaller internal column diameter. So this is a table of different reducing column inner diameters and then the associated lower flow rates, all kept at the same 7,000 bar pressure. And what we've done is calculated the power. And the trouble is, you can see that at 2 mils a minute on a 4.6 millimeter ID column, this is assuming a 1 micron particle packed in a 50 centimeter long column, you would generate enough power to boil the mobile phase before it exits the column. So when scientists had found this, they realized if we go to the smaller IDs where the pressure drop still is the same, but we're running at those lower flow rates, the power isn't nearly as high. And that in effect takes care of those two axial and radial thermal gradients that you see. So now I want to talk about the impacts on peak signal when you go to smaller internal column diameters. So the internal column diameter, really what we're trying to say is most LC detectors are concentration sensitive. If they're using a UV or a PDA detector, that limit of detection is going to be improved when the LC delivers a highly concentrated sample. And what you want to see is minimized dilution from the mobile phase. So of course, the flow rate optimum scales with the ratio of the square of the radius of the column. For example, if you take a 4.6 millimeter ID column and go to a 1 millimeter ID column, the original flow rate of 1 mil per minute on a 4.6 would scale to around 50 microliters per minute. And what that would give you is a 20-fold enhancement. Now, that calculation is based on the identical sample load, which means we're using the same sample concentration and the same injection volume. So I have a few examples here. We're looking at the absorbance with varying column diameter. So first, for a 2.1 millimeter ID column, you can see we're maxing out at about 0.25 absorbance units for the tallest peak. Then when we go down to a 1.5 millimeter ID column, that max signal goes up to 0.35 absorbance units. And then finally, if you go down to a 1 millimeter ID column, you get 0.47 absorbance units as the maximum. So we're seeing that signal increase as the column ID decreases with the identical sample load on column. So if it were that easy, you would be probably thinking, why doesn't everybody run really small ID columns? Well, we have to be aware of extra column effects. So what I mean by that are the sources of extra column band broadening. So this sigma v squared total, this is the total dispersion of the system. And that's everything that happens pre-column, including the sample injector and this pre-column tubing. And then also the post-column tubing and whatever your detector is or your ionization source. So these yellow and red areas are where you have the extra column band broadening. And this can really impact the actual separation that you see from your analytical column. So you can imagine as you go to smaller ID columns, the volumes of the peak become very small and then become more susceptible to the extra column band broadening. So here are the pros and cons in shifting from a 2.1 millimeter ID to a 1 millimeter ID column. So this plot on the left here is a separation of alkylphenones, and we've run it on the 2.1, a 1.5, and a 1 millimeter ID column. So the problem is, as you go to those smaller ID columns, they are more susceptible to the extra column dispersion. And even though the signal is higher, the peak is actually broader. And that's why the efficiency here is suffering. So the 1.5 is a way to sort of bridge that gap between, having to go down to the really small capillary ID columns and capillary systems, and you still get the benefit of that 1.5 millimeter ID column. So as a summary for this first portion, smaller ID columns are less subject to the effects of viscous heating, and then smaller ID columns offer the benefits of increased signal and reduced solvent consumption. To realize the benefit of that increased signal, the impact of extra column effects of the UHPLC and or mass spec system being used must be minimized. So now I'd like to introduce a new dimension in separations. And what we mean by the new dimension is our new Halo 1.5 millimeter ID columns. And with this new Halo 1.5, we like to say we're bridging the gap between analytical and microflow. So as hopefully most people are aware, Halo particles were introduced in 2006. And we were really excited because that enabled people to use their existing LC systems, but see higher efficiencies compared to sub 2 micron fully porous particle packings. Of course, since we were using a 2.7 micron particle size, the back pressure was not as high as what you would see with those sub 2 micron fully porous particle columns. So now with these new 1.5 millimeter ID columns, we have something that's good for the optimized UHPLC systems in terms of sensitivity, and you also get the benefit of reduced solvent consumption without the investment of specialized instrumentation and those more challenging, capillary separations. So what benefits are we talking about here? Well, we'd like to say that you'd get more performance from your UHPLC and LCMS systems. So more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LCMS systems, reduced solvent consumption compared to 2.1 millimeter ID columns and greater. And of course, that reduction in solvent savings also applies to disposal cost and creating a smaller chemical footprint. An easy to implement microflow solution with existing systems. And the Halo 1.5 is produced in our ISO certified facility with strict quality measures. So now I'd like to take you through some examples. In this one, we're looking at more sensitivity from conventional UHPLC systems. This is a comparison of a gradient separation of over-the-counter cough and cold medicines. So in the orange trace is the signal from the 1.5 millimeter Halo C18 column, and the blue trace is the signal from the 2.1 millimeter Halo C18 column. And we're seeing areas that are 2 times larger with the same injection and concentration injected on both columns with the 1.5. And our peak heights are 1.7 times taller with the 1.5 millimeter ID column. In this case, we're running the 1.5 millimeter column at 0.2 mils per minute, and the 2.1 is run at 0.4 mils a minute. This is an example using a gradient separation of peptides and small proteins. So again, the 1.5 millimeter is in the orange trace, and you can see the peaks are sharper and taller compared to what you have on the 2.1 millimeter ID Halo C18 column. And again, the areas are on average about 2 times as big on the 1.5 millimeter ID column. And of course, the peak heights are also increased. So for people doing impurity identification, perhaps going to a 1.5 millimeter ID column would be beneficial for them. In this example, we're looking at a comparison of a few same subset of the cough and cold medicines, and then salicylic acid as an impurity of aspirin. So here on a 3 by 100 Halo C18 column, we're getting pretty low response for the salicylic acid, right below 25 milliAU. And then when we go to the 1.5 millimeter ID column, we're getting much better peak area and peak intensity. So both the peak area and the peak height are increased. Now let's switch gears and talk about some higher ionization efficiencies from LCMS systems. In this example, we're using intact trastuzumab using the Halo 1000 angstrom diphenyl under gradient conditions. So the top tick here is showing the 1.5 millimeter ID result run at 0.2 mils per minute, and the bottom is the 2.1 millimeter ID column run at 0.4 mils per minute. So the area is 2.9 times larger on the 1.5 millimeter ID column, and of course the peak height is increased. We see the same effect when we look at the reduced and alkylated trastuzumab using the Halo 1000 angstrom diphenyl. In this case, we're looking at the light chain and the heavy chain. Again, the results on the top are for the 1.5 millimeter ID column. So the light chain area is 2.7 times larger than what you see on the 2.1 millimeter ID column, whereas the heavy chain is 2.3 times larger compared to what you see on the 2.1 millimeter ID column. Here's an example using norfentanyl and fentanyl. So on the left-hand side, we're looking at the results of the 2.1 millimeter Halo C18 column. And on the right-hand side, you can see we're getting 2.5 times gain in intensity and 2.4 times gain in area for norfentanyl. And then similar gains in intensity and area for fentanyl using the 1.5 millimeter ID column. In this case, we needed to optimize the source conditions for running at a lower flow rate on the 1.5 millimeter ID column in order to see these intensity and area gains. We've also observed higher ionization efficiencies with the vitamin D metabolites. So the data on the left-hand side is from the 2.1 Halo C18 column. And the data on the right-hand side is for the 1.5 millimeter ID column. So you can see for the 25 hydroxy D3, the intensity is 3.1 times larger, whereas the area is 2.9 times larger. And then for the 25 hydroxy D2, the intensity is 2.3 times larger, and the area is 2.2 times larger. So the intensity isn't quite the same for each compound. It all is compound dependent and how well each one ionizes. So then, since we're running at our lower flow rates, we're able to reduce solvent consumption compared to 2.1 millimeter ID columns. In this example, we're looking at a peptide map of trastuzumab run under gradient conditions. And so for this particular runtime, we're using only 12 mils of solvent compared to 24 mils for the 2.1 millimeter ID column, which would give you 50% solvent savings. And you're also seeing those larger intensity peaks on the 1.5 millimeter ID column. I know it gets a little bit hard to do the comparison here because the peptide map is very complex, but you can see that the 1.5 has taller peaks compared to the 2.1. We also compared versus the 4.6 millimeter ID columns, and this is using an isocratic separation of 13 cannabinoids. So in this example, you're using 15 mils for the 4.6 by 150 millimeter column, operated at 1.5 mils per minute, compared to only 1.6 mils of solvent for the 1.5 millimeter ID column, operated at 0.16 mils per minute. And you can see what that gives you is 9.4 times solvent savings. And of course, you're seeing those much larger, taller peaks on the 1.5 millimeter ID Halo C18 column. And one more example of reduced solvent consumption. So in this case, it's giving the example of modernizing methods. So we took the original USP method for estradiol, which calls for a column of 3.9 by 300 millimeter dimension, run at 1 mil per minute for a runtime of 8 minutes. That will give you a total volume of 8 mils. And what we did was we changed the method to be run on a 1.5 by 100 millimeter length column, run at 0.2 mils per minute for only 1.5 minutes, and that gives you only 0.3 milliliters of solvent used per injection, which represents a 96% solvent savings. So this is, I know it's a bit of an extreme example, but it does really show the impact of going to the smaller ID column. Now I'd like to talk about a few stability examples. In this case, we took a Halo 1000 angstrom diphenyl column and we ran it at 600 bar for 1,000 injections. And you can see that there wasn't any change in retention time or back pressure or efficiency across those 1,000 injections. So this shows that the hardware and of course the phase are both stable, run at 600 bar for 1,000 injections. Similarly, we ran the Halo 90 angstrom C18 column for 1,000 injections, also at 600 bar, and you can see over the course of the retention factor versus injection number, the percent RSD was only 0.28%. And that's just showing how, instead of showing the chromatograms, we're just showing the plot of stable retention across all of those 1,000 injections. Then in terms of the 1.5 millimeter ID column hardware reproducibility, we're showing excellent reproducibility from 3 different lots of column hardware, and we've represented these lot A, B, and C by the black, red, and blue traces here. We're using the example of the over-the-counter cough and cold medicines, and here we found retention time percent RSDs were all 1% or lower. So you can see if you had some doubts about, well, this is new hardware and I don't know whether I can trust it, this example I think would put those fears to rest. So then finally, our easy to implement microflow solution. The column looks and feels like a standard 2.1 millimeter ID column. They have stainless steel bodies and end fittings. So for a successful implementation, you would need to have an optimized system, and that includes both the hardware and accessories. So in terms of success using the Halo 1.5 millimeter ID columns, you'll need to have a UHPLC system with minimized extra column dispersion. In order to minimize those dispersion numbers, you'll need the right connectors. And then finally, successful method transfer to the 1.5 millimeter ID column. So I'd like to talk about variance charts for under gradient conditions here. Last year, Dwight Stoll, Thomas Lauer, and Ken Broekhoven had a nice 4-part series about the impacts of extra column peak broadening in LCGC North America. And in addition to their article, they also have the link for their dispersion calculator. And the nice thing about this is you are able to input your own tubing connector lengths and IDs and the parameters for your column and whether it's a gradient or an isocratic run, and it'll generate these plots for you. So what's being plotted here when you're running gradient conditions, it has the dispersion from the column, which is represented by this yellow wedge, the post-column tubing, which is the blue wedge, and then any dispersion from the detector is this gray wedge. So what I'm showing the corresponding chromatogram here for our standard UHPLC system, we were getting for peak 8 a height of 66 milliAU and a width of 0.046 minutes. And what we can do is optimize the system by changing out the connecting tubing to shorter IDs, smaller IDs, and shorter lengths. And what that does is it really maximizes you want most of the dispersion to be coming from the column rather than outside of the column, because this is what's going to give you the real true column performance. And in so doing, we're able to increase the peak height up to 105 milliAUs and reduce the width to 0.037 minutes. So for gradient separations, that would translate to increased peak capacity since the peak widths are smaller. And then we're able to offer the Marvel Exact connectors from IDEX. The difference between a Marvel Exact fitting and a ferrule fitting is shown here. So the nice part about the Marvel Exact connectors is that they have no ferrule, it's just a flat sealing face. And so you don't have any zero dead volume potential there. Whereas sometimes if you're using a ferrule fitting, sometimes that capillary doesn't bottom out to the bottom of the inlet of the column, And what that could mean is there'd be some extra internal volume, and that could impact your efficiency or peak shape. So these are available in both peak seal and peak line stainless steel options. The peak seal is good for going from the outlet of the column to the mass spec source. And then the peak line stainless steel, if you need to change anything from your sample injector to the inlet of the column. That's what we had done. And then the volume is included with the dimension for easy selection. So for instance, a 75 micron by 600 millimeter connector has a volume of 2,650 nanoliters. So how do you transfer a method to 1.5 millimeter ID column? The first thing you need to do is scale the flow rate. So I have the equation here where F2 is the scaled flow rate for the 1.5 millimeter ID column. F1 is the original flow rate. D2 is the column ID being transferred to, or 1.5 in this case, and D1 would be the original column ID. And then here are some calculated flow rates going from a 4.6 millimeter down to the 1.5. And then we included the 1 just so you can see how really small these flow rates are, and not really attainable by standard UHPLC systems. If you're running a gradient method, you would need to add an injection time delay to account for the dwell volume. And then you would also need to scale the injection volume to maintain the signal or keep the same injection volume for increased signal. So the examples that I have shown in this presentation all use the same injection volume for the comparisons. So you still have the benefits of fuse score in a 1.5 millimeter ID column. In this example, we're running at 0.2 mils per minute for the orange trace on a 1.5 millimeter ID column, and that's generating a back pressure of 268 bar for the over-the-counter cough and cold medicines. So when we take that same column and run it at double the flow rate, 0.4 mils per minute, and increase the back pressure to 524 bar, you can see we're getting the separation 2 times faster with minimal loss in resolution. So our critical pair resolution here was 5.4 at the slower 0.2 mil per minute gradient, and it only drops down to 4.3, which is still, clearly baseline resolved at 0.4 mils per minute, and we're able to get that separation done in half the time. So we have the chemistries and pore sizes available for both, or for small molecules, peptides, and proteins, and that's what these 4 products are intended for. The Halo 90 angstrom C18 is for small molecule separations. The Halo 160 angstrom ESC18 is intended for peptide and small protein separations. And then the Halo 1000 angstrom C4 and 1000 angstrom diphenyl are intended for protein separations and monoclonal antibody separations. So in summary, I've shown examples of more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LCMS systems, reduced solvent consumption compared to the 2.1 millimeter ID columns and larger, an easy to implement microflow solution with existing systems. It's made by a trusted manufacturer of fuse score columns in a 9001 ISO certified facility, and it's available in chemistries for small molecule, peptide, and protein separations. And I'd like to thank Jim Grindius of Rowan University and Justin Godino of GSK for their collaborations in helping us with the development of the 1.5 millimeter ID column. With that, I'd be happy to take any questions you might have. And I have the email address for MacMod if you have any questions you'd like to email to them.
Thank you, Stephanie, for that great presentation. We do have some time to answer questions from the audience. I want to remind everyone that you can type any question into the question window. So I'll give you maybe a minute to do that, and then we'll carry on. Okay, first question. Stephanie, what's the maximum amount of extra column dispersion that a 1.5 by 100 millimeter column can tolerate?
Okay, sure. So it really depends on whether you're running a gradient separation or an isocratic separation. In our case, we had measured dispersion to be about 2 microliters squared, and that was for a retention factor of about 6. So I would say anywhere from 2 microliters squared or lower, you would be in a good position to get the most out of the 1.5 by 100.
Okay. Oh, here's a great question. Isn't it true that smaller ID columns have lower efficiency?
Yes, a lot of people think that. So we had worked really hard to optimize the loading of these columns, so they're not showing as drastic of a reduction in efficiency as you might expect. So the data that I showed earlier, where the efficiencies were almost the same as a 2.1, that's real data. So we're really happy with the efficiencies that we're getting out of these columns, and have to say we're pretty proud of that.
Here's another one. Let's see. For standard waters H-class UPLC with a typical install and plumbing, can the extra column volume pre and post column be reduced any further, i.e. is there any narrower tubing?
I don't know how an H-class comes standard plumbed, but I do have references where they have, I think it was for an H-class, where they have gone to smaller ID and shorter length. I think they're also maybe able to change the sample loop, but if you email me, I could give you the reference.
Okay, great. Would you still see an increase in performance on an unoptimized system?
I think you would, but it depends on how unoptimized the system is. So you'll definitely see the solvent savings if it's an unoptimized system. It's really going to depend if you see as sharp peaks as you might like, but I think you'd still see some benefit, maybe just not as drastic.
And then what is the effect on sample loading when moving to a 1.5 millimeter ID from a 2.1 millimeter ID column?
Well, of course, it's the column bed size is reduced when you go to 1.5 millimeter ID column, so it squares with the ID, just like you have to square it for the flow rate and for the injection volume. So it is going to be reduced by about half.
Okay. That seems to be the last question. If there's any other questions, I'll give another 20 seconds. For our lab, when we use a 1 millimeter ID column scaled from a 2.1, we typically see the 4.4 times increase in area. However, we only really see about 2 times increase in height and 2 times decrease in width. With that, is there any reasoning to that, and how would a 1.5 millimeter ID column help?
Oh, sure. So they were probably not seeing as much of an increase in height because of the dispersion of the system. It also depends, are you running under gradient conditions or isocratic conditions, because the retention factor can also have an impact on that. But the good news is with a 1.5 millimeter ID column, it's not quite as susceptible to extra column effects as a 1 millimeter ID column. So,
And then, do you see any retention shifts due to the analytical pump on the 1 millimeter when we try to run it on a standard HPLC versus a 1.5?
I think it might. Well, I think when you go to the 1.5 and the 1 millimeter ID columns, the mixing becomes very important. So we probably would recommend having a smaller mixer if you're using a smaller ID column that could potentially impact the retention.
Okay. Well, unfortunately, that's all the time we have for today. If you did ask a question that we did not get to, we will follow up with you via email after the fact. On behalf of MacMod Analytical, I want to thank Stephanie for a terrific webinar, really terrific webinar. Thank you all for attending, and we hope to see you all soon on future webinars. Goodbye.